In this video I will show you how to create a linear model in OpenStats. You can create statistical models by using the formula editor, which can be opened here clicking this button. It is available within each tab. An exception is the data wrangling tab, because here the UI already has many elements and it would be distracting. But for now, let's click Open Formula Editor, and within this frame we can choose the model type, and it's optional, and the default type is the linear model, so we don't have to change anything here. But what we have to change is we have to choose the dependent variable. The dependent variable is it's the variable on the y-axis, so it depends on another variable which will be later defined. For now we say, okay, we want to see how the uptake of CO2 by plants is affected by, and now we have to choose the right variable. We choose the concentration as a predictor, so the concentration of CO2 in the atmosphere, and we want to know how the concentration affects the uptake of CO2 by plants. You can also add more than one predictor by using these operators like plus or times. If you are interested in how to do this, please check the documentation. Every tab and every window has a question mark operator, and by clicking it you will see the documentation, which will give you a little bit about the theory behind it and how to use the app. But for now we are fine with uptake independence of concentration, and we click Create Statistical Model, and on the upper panel of the Formula Editor we see now the statistical model as statisticians would write it down. So we have the uptake, and the uptake is predicted by alpha plus beta 1's concentration plus epsilon. Epsilon is the error, beta 1 is the slope, and alpha the intercept. So we can close the formula editor now, and we already see that the current model is now of type linear model, and its uptake independence of concentration. This is a simplified formula description of way statisticians would write it down. Besides this, we have now a description, a summary of a model. First of all, we see here the model summary 2. So 2 is the number, it's just a counter which is incremented each time a result is added to the result list. And as we see, the data frame is at the first position, and here now the model summary is the second entry in the result list. It's the chronological reverse of all results which are produced. In the upper panel we see the visualization of a statistical model, so we see the predicted uptake and how it depends on concentration, and with increasing concentration we see an increased uptake, so this makes sense for us. Besides the visualization we also have a summary. In the summary you see here two terms, intercept and concentration. The intercept is the alpha of the model, and the concentration, don't get confused, this is basically the slope parameter. So we see we have here an estimate of 90.5 for the intercept, and we see that the concentration is 0.017, not the concentration, the slope, sorry. For both parameters we have calculated a standard error, furthermore a t-statistic value and the corresponding p-value. If you want to compare more than one model, you can use this by information criterion like AIC and BIC. A rule of thumb is that the lower the better the model, as long as it can explain what you are interested in. So these values are only interesting if you want to compare one model with another one. So, and with this I come to an end, because we have now created a linear model. In this video I will show you how to test assumptions. So after you have created a model, in this case it's a linear model, and we see here the predicted length of sepal leaves and how they depend from the three different species: Setosa, vesicolor and virginica. So if we want to know whether there is a statistically significant difference between these three species for the sepal length, we have to conduct an ANOVA because we have more than two groups. So first of all, we have to create a Shapiro test for the residuals, as we only have one predictor. The Shapiro test tells us whether the data is normally distributed or not. So whether the residuals are normally distributed, and we have here a statistic value, we have here a p-value of the method which was used, which is the Shapiro test, Shapiro-Wilk test, and we have another column, which is the column actually which is interesting for us: residuals normally distributed, and it's true. So we have so this assumption is met. We have normal distributed residuals. Beyond the normal distribution assumptions, we have also the assumptions of variance homogeneity. So we have a possibility to conduct a so-called Levene test. After conducting the Levene test, we see that again we have here pretty similar values, and in the last column we have variance homogeneity, which is in this time false. So this assumption of variance homogeneity is not met. Beyond the tests, we can also use visual tests to create diagnostic plots, because these take a lot of time. We see here that they are in the process, it's running, and if you want to stop it, you can press the stop button if it takes too long, for example. But now it was pretty fast, and as we can see here, we see here the QQ norm plot, and as you can see that the dots are more or less on the same line, which is a good sign, because it means that they are normally distributed. When we see here the residuals versus fitted values, and if it's the case, if they form like a tunnel, so if they go, if one group is bigger than the other, then it's a sign that we don't have variance homogeneity, and we already know from the Levene test that it's not the case. So we cannot conduct here an ANOVA. So thank you.
In this video I want to show you how to run statistical tests. So we have created a linear model in the last video, and we run several assumptions tests, and as we saw, we have not met the criteria for the variance homogeneity. Therefore we cannot use parametric tests, but still we can figure out whether there is a significant effect between the groups. So we can go to the test section, and here we have more than two groups. We have here, we can choose the test family. We should use the non-parametric test family. As I said, we haven't met the assumptions for the parametric tests, but just to show you, if I click on the parametric one, we have here ANOVA and bulk ANOVA, but for now we go with the non-parametric tests. And here you have two choices: the Kruskal-Wallis test and the permutation ANOVA. We will go with a Kruskal-Wallis test, and we see we have a very small p-value here. So we can assume that there is a significant effect due to the different species, which is great, this is what we wanted to figure out. And the next point would be, okay, which species differ significantly from each other? And to do this, we can go to the multiple comparison tab. And within the multiple comparison tab, you have two main groups here: the post hoc tests and the pairwise comparison. So for postdoc test is again you should use the Kruskal-Wallis postdoc test as a non-parametric alternative to the parametric ones, and we have a balanced design. The p-value you can adjust, but for now 0.05 is pretty fine, and also the adjusted p method is fine. So let's run the test, and we see here the three in each row we have a result of one species: Virginica, versicolor, and setosa. Sepal length is the mean values of the different species. So we see that Virginica has the highest, versicolor is in between the two others, and setosa has very small sepal lengths. And we see here also these letters, and it's basically if one group shares a letter with another one, then these groups are not significantly different from each other. But here we have ABC, so the groups differ statistically significant from each other. An alternative is to use here the pairwise comparison, so you run the Wilcox rank sum test several times, but you have to adjust the p-value. I can just show you how this would look like. Basically, you have here the comparison of versicolor with setosa, Virginica with setosa, and Virginica with versicolor, and you get a p-value for it each time. So these are the methods to compare here the groups between each other. Just for completeness, I want to say that if you have only two groups, then you have here also a third tab, and this tab allows you to run a t-test in case you have met the assumptions for the parametric test, or a Wilcox rank sum test in case you have not met the assumptions.
In this video I want to show you how to save the results, either in the local version or in VLN. It's the same. So you have here the result list, so the results in reverse chronological order. And now you go to the top of the results list, you choose a file name, let's call it results.xlsx, and then you press save. If you're using the local version, then you get an Excel file downloaded. Otherwise, the results.xlsx file is sent to VLN. So I press save now. In this video I will show you how the results are structured. So in the last video you saw how we saved the results from our analysis into an Excel file. And within this Excel file it is always the same format. So we have at the beginning the so-called history table. In the history table you have listed all the steps you have done. So the first step is the version step, which is not important for you, but later we are coming back to it. Then we have set active table, which is the default one because we only upload one data set. And afterwards we created a formula. The formula was linear, so there are no further details needed. This is only used for other types of models. And we have sepal length independence of the species. Afterwards a model summary is created. So the model summary is the first result after the actual dataset, so let's scroll over it. And here we have the model summary, we have here the visualization, we have here the table and the AIC and BIC value. I go back to the top because I want to go through all of these different steps. Afterwards we have conducted a Shapiro test to check if our data of our residuals are normally distributed, and we have checked whether we have variance homogeneity. We didn't have it, and therefore we also conducted a diagnostic plot, and this was confirmed also for results of step 3 and 4. And therefore we didn't use an ANOVA, but instead we used the Kruskal test, and also for the postdoc test this was true. If I go down now, so you have here the the same text as stated in the history table in the result column. We have model summary, we have Shapiro and residuals, we have here the Levine test, we have the diagnostic plots, we have the 2K, sorry, not the 2K, the Kruskal test, and then we have the Kruskal postdoc test. And then we have one more field, and this is the so-called history. And this history is not the same as the history table at the beginning, but it's the history for computers, so it's non-human readable, and I will tell you in the next video how you can use it to replay your entire analysis. Next, I will show you how to replay your entire analysis. First of all, you have upload the data you have used in your analysis. So this time I have uploaded the iris dataset, so we have sepal length, sepal width, the same for the petal leaves and how they depend on the different species. Next, you choose the history tab, and within the history tab you have here now a text file called history JSON. And within this history JSON file you just paste the last entry in of results, which is the history in JSON format, so for computers. Afterwards, you press the replay history button. You will be asked whether you are sure, because everything will be overwritten, so only do it if you are absolutely sure. And then I press here yes, override the entire history. Now it's running in a background process, so you can interrupt it at any point, but then you will of course lose the result, so you don't get a result back. But as we see, we have here or I'm seeing a message that the result was successfully replied, and we can see we have here the model summary. Then I go up and we have here, for example, our diagnostic plot, and here the Kruskal test and the Kruskal postdoc test. And this is helpful if you want to replay your analysis without doing all the steps by hand. And it also has the benefit that you can proceed now from the result, from this step.